you should now all see the front page of Fundamentals of Digital Technologies. So this slide covers the main parts of the organization. CI 103 gets you self-enrolled in Moodle. I hope you all know how to access the Moodle site, right? And all meetings throughout the whole semester, as far as the current plan goes, going to be by WebEx meeting. We're going to use a textbook. The cover page is shown here. It's Digital Design and Computer Architecture by Harris and Harris. I'm going to abbreviate it as H&H for Harris and Harris from now on. You're going to get a library ebook for free, right? Although I believe there is some document right on it so that you can't keep it forever. Now, the slides that I'm presenting to you right now, I will make available after the lecture on Moodle. So you can download the slides that I'm showing you from Moodle shortly after the lecture. The same goes for the exercises. There will be weekly homeworks, problem sets that we're going to discuss in class. I will publish those problem sets and brief solutions via Moodle. In addition, I'm going to offer you warm-up exercises, in particular for those of you who feel they need a little more exercise or are not particularly familiar with digital design yet. You may want to consider looking over the warm-up exercises first before you start working on the problem sets. And I'm going to say a little bit more about that in the exercise session that follows after this lecture session. The exam, given the current plan, modulo corona unknowns, will be an analog closed book exam somewhere in a classroom on campus. It will be 90 minutes long, and it will cover problems that are very comparable to the problems on the problem sets. So use the problem sets to check your own knowledge, right? To prove to yourself that you know that you've learned the material. If you are able to solve the problem sets, you should be able to pass the exam. All right, this is the main part of the organization. Let me now speak a little bit about our special semester, namely that we're using an online classroom, and mention a little bit on the etiquette of live online. First of all, I am giving you live online meetings as opposed to canned video, because I believe it's more important than that you can ask questions than anything else. The exercise session will be pretty much like the lecture session, right? We're gonna meet online in this classroom. I'm gonna discuss the solution to the problem sets that I handed out a week ago. So next week, I'm gonna discuss the solutions to the problem set that I'm gonna hand out today in the first exercise session after this lecture, which will be reasonably brief because that's essentially all I will be doing. I am recommending highly that you solve those problem sets in advance so that you can ask qualified questions when we meet to discuss the problem sets, right? If you don't have any questions to ask, it won't be a discussion, but it will be just a presentation from my side, and the learning effect that you take away from that is going to be significantly smaller than if you come prepared. Now, I also recommend that you consider forming study groups, small study groups where, say, 2 or 3 of you meet, perhaps online. You can use WebEx to accomplish this or any other conferencing system that you like. The advantage of studying in a group is mainly that you have to discuss the material, and just talking about the material using the special technical terms is the first big step into learning a new topic, right? On the other hand, I would recommend that after you have gone through the problem sets in your study group, write down the solution all by your own. This will give you confidence into whether you actually really understood every detail of a problem. If you do, you should be able to pass the exam. If you don't, there are 2 more options. Right? Option 1 is to look into the warm-up exercises, and I will hand out the first set of warm-up exercises, like the first problem sets later on today, and gonna discuss these warm-up exercises then after this lecture. And the second option you have is to get more confidence in the material by looking into the textbook. And I will give you the solutions to all odd-numbered exercises in the textbooks. These are the official solutions published by the author after this lecture when I will upload them to Moodle. So you can download the solutions to all odd-numbered exercises in the textbook if you want more practice solving problems related to the material that we're going to discuss. Right? So much about the online etiquette. And this will be the syllabus that we're going to cover this semester, and according to the current plan, there will be 25% of the lectures falling victim to Corona. The last 3 that I've stricken through and read, we will probably not be able to cover, but well, this is still up to future decisions, not only by the university, but also by politics. So until we get there, for the time being, be aware that this class will cover less material. You can think about this one way or the other, right? You have less material that you need to prepare for to sit in the exam. On the other hand, you are missing something, right? And you're going to be missing a interesting topic, the microarchitecture topic in particular, that connects the computer architecture part, which is the software world of digital design, and the hardware part, which is covered by the first 7 lectures of this class. Now, even if this current plan stands and we cannot cover the last 3 lectures, I believe that if we just cut out the last 3 lectures, you should know essentially enough to study microarchitecture with the help of the textbook by yourself. If you want to know that material, you should be able to do it. Right now, if not, then if you want to know about it, perhaps there was a chance to sit in next year again. But all of this is subject to speculation. All right, so today's lecture will start with a recap for most of you guys. namely number representations, except that number representations after this lecture are such a basic skill that you need to know about, that you better know about it, because we're going to use it in all different types of facets from lecture 2 on. So in that case, I assume everybody knows roughly what this class is going to be about, right? And I'm going to start essentially with the hardware portion, the digital design portion of this year's semester. So let me begin by showing you the hierarchy or the stack of different areas that the design of digital systems involve these days. This is perhaps one of the most complex system design exercises mankind has achieved. Right? It starts at the bottom with physics, where if you really would like to know how a digital system works, well, you better know how electrons behave at the electronic level, right? And it goes up all the way to the application software, which are programs that probably all of you guys know how to write already. And there was a lot in between. Okay, so in this class, the first 7 lectures, we essentially cover 2 levels. The digital circuits level, where we talk about gates, like AND gates and inverters, and the logic level that uses gates to implement logic blocks like adders or memory. Then in the very shortened second part, which now just includes lectures 8 and 9, we're going to look at computer architecture. We're going to look at how instructions and registers, visible hardware elements to the programmer, are actually being used from the software programmer side. Right? And the original plan would also include moving back into the connecting layer, the microarchitecture that is hardware, right? And it tells you how to organize logic blocks like adders and memories to implement an architecture, to implement an instruction set of a computer. Right now, unfortunately, we're probably gonna not get there, but there is still enough opportunity in the 3 layers that we are going to cover to understand one very important principle that is used to manage complexity in such complex systems, and that is the art of abstraction. Right? The art of abstraction is to hide details of one layer in this hierarchy so that you can work at the next higher level of the hierarchy without being completely overwhelmed by all the details at the lower level. For example, if you want to write an application program, the very top layer, and to do that would have to know how electrons move around across p-n junctions in transistors and memory cells to execute your program, where you wouldn't be able to write significant programs. And you would spend most of your time thinking about all those electrons flitting about. It's impossible to design complex systems that way. Instead, you're going to abstract away details, keep just enough around to keep yourself productive in a higher layer. And I'm going to show you the art of abstraction at work on one of the following slides. Actually, the next slide, excuse me. So Here is a particular type of abstraction, the digital abstraction. If you look around yourself, right, most physical variables that you perceive, like the position of an object yourself, right, or the weight of a mass, your body mass, or the voltage on a wire, the frequency of an oscillation, etc., all these are continuous measures. In contrast, if we look at digital measures, we do not consider those continuous values, but restrict ourselves to a discrete subset of the continuous values. Let me illustrate this by example, abstraction. Right? So here's my pen. Maybe the tip of the pen points to the 10 centimeter mark, right, on my ruler here. And now I'm pointing to the 20 centimeter mark of my ruler. Right? What have I done? I have just picked two discrete values, the 10 centimeter and the 20 centimeter position of a continuous length scale on my ruler, right? Even better, right? In three-dimensional space, right? There are many more than points than just on that one-dimensional subset. So I've just picked two positions for the tip of my pen object, right? Now, what does it mean to do a digital abstraction? Well, the digital abstraction means we simply restrict ourselves to two positions of the object tip of the pen, right? If I want to move from one to another position, I can do this slowly on the straight line between the two, right? I can take a ripple pirouette with a garnished somersault, right? And move from one to the other, right? As long as I do this so fast that the time for which I stay in one of the two discrete positions is much longer, it doesn't matter how quickly I get in between and which path I took to get from one to the other position, right? So it may well be that I'm just interested in whether the pen is in position 1 or in position 2, or better in the digital world, I may give this position a name 0 and this position here a name 1, right? And if I move in between, that's fine, right? Eventually, I'm going to land on one of them and going to stay there, right? And you can identify where the pen is by telling me, well, the pen is in position 1, or the pen is in position 0, right? Trivial, but very important, right? This very simple idea of restricting ourselves from a three-dimensional space to just 2 points is the crux to accomplish many things, and one of them is to build digital systems, right? So back to our slides, and this fellow here, Charles Babbage, is credited with building the first digital machine. And he did it by using mechanical gears, as shown here in the bottom right, where each gear represented a digital value, 10 of them, the 10 decimal digits, 0, 1 up to 9, and was able, or actually was almost able, to run computations on this mechanical machine. Now I'm saying almost because he unfortunately never managed to finish the machine, right? He worked on it for almost 40 years and passed away before it was finished. That should give you an idea how difficult it is to realize a Babbage did a lot of work on his machine, right? And you never know, nobody actually knows whether he really grasped the principle of digital abstraction. If he did, he probably would have been able to build this machine much faster, right? But, well, we'll never know. He is dead for 150 years by now. So today, we consider digital abstraction to work with just two discrete values, unlike the 10 that Babbage used at his time, namely the two discrete values 0 and 1. In a discrete circuit, in a digital discrete circuit, right, 0 is typically represented by a low voltage and 1 is represented by a high voltage. And a bit is a binary digit, the analogon of a decimal digit, which may have one of two values, 0 or 1. Now, to manipulate bits in a mathematical formalism, George Boole, whose portrait is shown on the right, introduced what's now known as binary variables. And he also introduced the basic logic operations, and or XOR not. And there is a nice copy of his investigation of the laws of thought, which was considered a philosophical piece of work back then, on Gutenberg.org. Unfortunately, Gutenberg.org is blocked for legal reasons within Germany, but I guess you all know how to circumvent these kind of internet snakes of the day by using the Tor browser, for example. Check it out. It is still a good read about the basics of logic. Now, logic will come in very prominently. Before I cover logic, I will be reviewing number systems. So here is a decimal number, 9,742. Right? What is that? Well, it is essentially nothing but a juxtaposition or a concatenation of 4 decimal digits. The decimal digits are 0 through 9. We are all familiar with it. Your parents trained you to learn the decimal numbers, right? And besides the digits, make sense of a decimal number like 9,742, right? You associate a value with that number. Depends on the context, right? If you look into the context of monthly salary in euros, then you know immediately that 9,742 is a pretty good salary, right? If you look at it from the perspective of, say, your savings for a trip to Mars, well, it won't get you far, right? The latest guess or the latest announcement by Elon Musk to fly to Mars with one of his SpaceX spaceships is about $500,000, right? And $9,742 won't get you even close there. Right? But besides this informal notion of value attached to a number, what is it really, right? What it really is a very skillful encoding of a value such that the rightmost digit counts once, the digit to the left of it counts tens, the third digit counts 100s, the fourth one 1,000s, and so on, right? And you can write this count as a weighted sum, according to which the 2 counts ones. There are 2 ones. 1 is 10 to the power of 0, and anything to the power of 0 is 1. The 4 counts tens. 10 equals 10 to the power of 1. The 7 counts hundreds. There are 7 hundreds written as a power of 10. That's 10 to the 2 equals 100. And the thousands are the third power of 10, right? So you can see that there is a very simple relation between the value of a number calculated as taking the digit in the corresponding position and multiplying it with 10 to the power of that position. Right? Now, the same principle goes for binary numbers, except that if I am showing you a binary number 10110, you probably are not able to associate a value with that, right? If I offer you a job and your salary is going to be 10110 binary, you probably don't know whether that's a good or a bad salary. However, you can figure out what the value is by converting it into decimal using exactly the same principle that we use for decimal numbers. Binary numbers, however, have only 2 digits, the bits 0 and 1. The rightmost 0 in this example counts ones, the next one twos, the third one fours, eights, 16s, and so on, because these are the positions raised to the power of 2. Right? 2 to the 4 is 16, 2 to the 3 is 8, 2 to the 2 is 4, and so on. Now, since you only have 2 choices, take a 16 or not, right? 1 if there is a 16 included, and 0 if not. It's actually pretty easy to evaluate this value, this weighted sum, right? There is 1 16, no 8, plus 1 4 is 20, plus 1 2 is 22, and no 1 remains at 22 in decimal. Right, so you probably should decline any job offers that offer you a binary salary of 10110. Maybe not if it's your hourly salary, but certainly not if it's your monthly salary. To work with larger numbers, it's definitely a good idea to get a handle of the powers of 2. Right? 2 to the 0 is 1, like every base raised to the power of 0 is 1. 2 to the 1 is also easy, that's 2. 2 to the 2 is 4, and so on. Right? When those numbers get really big, right, we use special notation like we use for physical units. Right? 2 to the 10 is 1 kilo in binary, and it's called 1 kilo because it's actually very close to 1,000, which is denoted 1K by physicists, except that 2 to the 10 is a little larger, right? 1,024. 2 to the 20 is 1 mega, 1 million. Actually, the power of 2 is a little bit larger than 1 million, and so on, right? Actually, the largest numbers that are interesting as we speak now are the peta and the exa. The peta equals 2 to the 50, or in direct powers of 10, this is 10 to the 12, right? In binary, again, a little larger than 10 to the 12 is 1 peta. And the reason why peta is important is that about 10 years ago, the fastest supercomputer on this planet managed to execute more than 1 peta floating point operations per second, flops. And as we speak, the base is on to build a supercomputer that is capable of executing 1 exaflops. which is 1 to the 18 flops, which is the number closest to 2 to the 60, and the extension will be 1e once we hit that. Okay? Now, the best way to deal with binary numbers is to remember the exponent rule in the bottom right corner of the slide. Write 2 to the a times 2 to the b for some positive integers a and b is equal to 2 to the sum of a and b. Right? That allows you to quickly compute powers of 2 that you might not remember. Okay? So let me show you how that might work. Right? If you should tell me what 2 to the 9 is, right? But don't remember, I don't, right? You may want to remember a few of those powers of 2's, like 2 to the 10. Right? 2 to the 10 is 1 kilo, and I happen to memorize that 1 kilo to be 1024. Right? Now, if 9 equals a, right, and we add 1 to a, we get 2 to the 10, right? 9 plus 1 is 10, that's 1024. The other way around, we will know what 2 to the 9 is by taking 2 to the 10 minus 1 and now applying the exponent rule. This is going to be 2 to the 10 times 2 to the negative 1, right? 2 to the negative 1, that equals 1/2. So 2 to the 9 is 2 to the 10 divided by 2, and 1024 divided by 2 is 512, right? Once you get used to that calculation, right, you can very quickly compute any binary number, any power of 2, that is, that you didn't know before, right? Now, I've shown you how to look at decimal and binary numbers. The principles by which we computed the value of a number happen to be the same, and they happen to be the same for all kinds of bases beyond 2 and 10. And this is what's called a general positional number system. If the base b is not fixed, you can still write a number simply by concatenating digits. Right? I call the digits a sub I, where I is the position in the number. We distinguish between integral numbers, integers, and fractional numbers. We separate those in our notation typically by a radix point, in Germany by a comma. In the English-speaking part of the world, we use a dot, the radix point, to separate them. The most significant digit is on the left end, the least significant digit is on the right end, right? And we can compute the value of a number to base b without referring to the base b explicitly. We typically know from the context which base we are referring to. When you are going to the cashier on the supermarket, right, the base is 10. Right? You cannot tell the cashier in the supermarket, well, I'm gonna return you 10110 euros, right? The base is 2, by the way, right? However, you can compute and represent any number, capital N, in a positional number system with base b by simply doing the same weighted sum that we did before And even going from positive through position 0, right, to the left of the radix point, seamlessly into the negative indices to cover the fractional part, right, which becomes very obvious if you write this weighted sum as a summation. The summation of the digit a sub I with position I times the base raised to the power of I, and you sum over position indices I from negative p to some q minus 1. So once you deal with different number systems, you may want to design digital machines that cover some base b, not 10, not 2, but some b, right? At which point it becomes interesting to know how many digits you need to represent an integer number, say capital N, right? The answer to this question in mathematical notation is written in blue on this slide. The number of digits that you need to represent number capital N is the log to base b of n plus 1 and take the ceiling of that, means the smallest integer such that capital N is less than base b raised to the power of q. Right, that's a mouthful. Let me illustrate it by two examples. Let's first look at representing a decimal number, capital N equals 42. And if you look at 42, it has 2 digits, so we obviously need 2 digits to represent this number. So q must be q2. But why is it 2? Right? If we had just 1 digit, then 10 to the power of q minus 1, 2 minus 1 is 1, is 10, which is not larger than 42. In fact, it's strictly smaller than 42. But if we use 2 digits, then b to the q, 10 to the power of 2 is 100, which happens to be larger than 42. Right? So with 2 digits, we can cover even larger numbers than 42, but 42 is also covered, and because it's not sufficient to have just 1 digit, 2 digits is the smallest number of digits necessary to represent decimal number 42. Now, what if we want to represent 42 as a binary number? That is, base is 2, how many bits do we need to represent it? The answer turns out to be 6. Why? 2 to the 6 happens to be 64, which is larger than 42. And the next smaller number of bits, q equals 5, is 32, which is not enough to represent number 42. So 6 is the smallest integer that is a power of 2, 64, larger than 42, and hence 6 is the number of bits that we need to represent decimal number 42. Right? This gets interesting if you look at the corner cases. I encourage you to discuss with your fellow students what happens if the number n, the decimal number, is equal to b to the q minus 1 or b to the q. But another question that comes up very often is how many integer numbers can q digits represent? Right? Let's look at decimal numbers at first. How many decimal numbers can you represent with 4 decimal digits? Well, one way to go about it is to enumerate them all, right? To form the set of all 4-digit numbers. The smallest one is 0, which when written as a 4-digit number is 0000. The next one is 0 plus 1 is 1. When written as a 4-digit number is 0001, plus 1 is 2, and so on, all the way up to 9,999. Right? Now, we obviously don't want to write large sets of numbers by enumerating all of them. A much more concise way of denoting such a set of numbers is the bracket notation for the range of number. We use brackets to enclose the smallest number in the set and the largest number in the set. Now, notice in this particular example that 9,999 equals 10 to the power of 4 minus 1. Right? 10,000 to the power of 4 is the smallest 5-digit number, larger than 9,999. So 10,000 minus 1 is the largest 4-digit number we can represent. Well, that observation generalizes. Right? If you have q digits for a number system with base b, you can represent all integral numbers in range 0 up to b to the power of q minus 1 with q digits. And the number of digits in this set, denoted by the range, is exactly b to the q numbers. Example, in the decimal number system, 10 to the q numbers are filling the range 0 up to 10 to the q minus 1, where if q equals 3, the number of integral decimal numbers we can represent is 10 to the 3, b to the q. Right? 10 to the 3 is 1,000, and the numbers are in range 0 through 999. Analogously, in the binary number system, right? There are 2 to the power of q numbers in range 0 up to 2 to the q minus 1. Example, when we fix q to be 3, there are 2 to the 3 or 8 numbers in range 0 through 111 binary. I'm using the subscript 2 to denote the binary number, right? And 111 is 4 plus 2 plus 1 equals 7. The largest number that can be represented with 3 bits is 7. All right, so now we know to deal with numbers with two different bases, right? Binary and decimal. And machines work with binary numbers. We as humans are trained to work with decimal numbers. So what we want to be able to do is quickly convert between the two. So here are the 2 types of conversions, first from binary to decimal and then from decimal to binary. The conversion from binary to decimal is simple. We have essentially discussed it already. It is the evaluation of the weighted sum, which is given the name positional conversion. Right? If you're given a binary number 10011, you convert it to decimal probably easiest by going from right to left, because the rightmost bit is always associated with position 0, right? And 2 to the 0, like anything to the 0, is value 1. The next bit is associated with position 1. 2 to the 1 is 2. The third bit 0 is associated with position 2. 2 to the 2 is 4. The next 0 with position 3. 2 to the 3 is 8. And the last one with position 2 to the 4. Position 4 and power of 2, 16, right? You can add these guys up, right? 16 plus 2 is 18, plus 1 is 19, and you got the decimal value. Now, the opposite is a little harder, right? The way to convert from decimal to binary, what we use is called successive division. And if you do it manually or by hand, right, you typically do it as I'm going to demonstrate now, right? If we want to convert 47 to binary, we first want to find the largest power of 2 that fits into 47. Right? Remember 64, which was 2 to the 6. 64 is larger than 47, so it's not the largest power of 2 that fits into 47, but the next smaller one, 2 to the 5, which is 32, fits, right? 32 is less than or equal to 47. So this is where we start the division, right? 32 fits once into 47, right? 47 divided by 32 is 1. So we remember a 1 bit associated with 32. And the remainder is 47 minus 32, 15, right? And we continue dividing successively the remainder, right? And we do it successively with the next smaller power of 2. 16 is 32 divided by 2 is larger than 15. So it doesn't fit into 15, means we have no 16. The next smaller power of 2, 8, fits into 15, however. So we have 1, 8, and the remainder of that division, 15 divided by 8, is 7, right? The next smaller power of 2 from 8 is 4. 4 is less than 7, it fits. So 7 divided by 4 is 1. We remember the 1 associated with the 4. The remainder is 3, right? 7 minus 4 is 3. 2, the next smaller power of 2 fits into 3 once. We remember the 1. The remainder is 1. 3 minus 2 is 1, right? And the last power of 2, 2 to the 0 equals 1, fits once into 1. So we have 1, 1 left. Now, all we got to do is collect all these ones and zeros in that sequence, right? And we got the corresponding binary number. 47 in decimal is 10111, binary, right? And you can see now why I'm very vigorous about using the subscripts, right? I annotate a number with the base of the number system in the subscript to ensure that I know with respect to which base I have to interpret that number. Except when I'm looking at these weighted sums where I'm always assuming that things are decimal. All right. So you can use positional conversion and successive division to go between not only binary and decimal, but also other bases for number systems, right? Here I've also shown you the octal and hexadecimal numbers. The octal number system uses base 8, the hexadecimal number system uses base 16, and I'm showing you the first 16 numbers in range 0 up to 16 to the 1 minus 1 is 50, right? Now, if we interpret these 16 decimal numbers as binary, or want to represent them as binary numbers, you want to know how many bits you need to represent the largest of these numbers. Well, you know how to do it, right? Q equals 4 in this case, and the binary numbers are listed in the next column. if you use octal numbers, the number of digits you need is Q equals 2. And the range of the digits in the octal system is from 0 up to 7. There are 8 different digits from 0 up to 7. Right? So 0 is 0, 0, 8 is 1, 0, 8 to the 1 plus 0 times 8 to the 0, and 15 is 1, 7 is 1 times 8 to the power of 1 plus 7 times 8 to the power of 0. The hexadecimal number system gets by with the fewest digits, namely Q equals 1. Right? In particular, the first 10 numbers, 0 through 9, are represented by the same decimal digits that we use for decimal numbers. And now we got a little problem, right? We are running out of decimal digits, right? Our writing system provides us with 10 digits, not with 16. And we borrow simply the first 6 letters from the alphabet to encode the hexadecimal values, 10 with an A, 11 with a B, up to 15 with an F. And this may be confusing at first, but once you play around with it, it's actually pretty straightforward, right? Now, the conversion from hexadecimal to decimal and the other way around works analogous to the conversion between decimal and binary, for example, right? Let me show you examples here for given hexadecimal number for a F to decimal. We do it by positional conversion, right? We expand 4AF from right to left, right? F is associated with position 0, so F has weight 16 to the power of 0. A, the next to the left, is associated with position 1, means weight 16 to the power of 1, and 4 with position 2, 16 to the power of 2. Right? We can calculate that. 16 to the power of 0, like anything to the power of 0 is 1. 16 to the power of 1 is just 16, and 16 to the power of 2, 16 times 16 is 256. Right? And the hex digit 4 is equal to decimal digit 4. Hex digit A is equal to decimal number 10, and hex digit F is equal to decimal number 15. We have a weighted sum, purely decimal, that we can evaluate to 1199. So 4AF in hex equals 1199 in decimal. The converse, or the other way around, works with successive division. As I demonstrated before, right, if we are given a decimal number 3098, and want to convert it to decimal, we start by finding the largest power of 16 that fits into 3098. There is one complication compared to binary conversion. Whenever the base is larger than 1, as it is for hexadecimal numbers, then the power of the base may fit more than once into the number, right? And it turns out that the largest power of 16, 256, fits 12 times into 3000. 12 times 256 is less than 3098, right? 12 times 256 is 3 times 4 times 256 equals 3 times 1024, right? That's 2 to the 10. You may remember that. And 3 times 1024, I can do by rote, right? That's 3072. So 3072 is less than 3098. So we get 12 times 256 in 3098, and the remainder is 3098 minus 372 is 26. Check. 26 is less than 256. The remainder has to be less than the divisor, right? Okay, it is. We continue with the next smaller power of 16, with a 6 into the 1, and 16 fits ones into the remainder, 26. Well, the new remainder is 26 minus 16 is 10, and the next smaller power of 16, 16 to the 0 is 1, fits exactly 10 times into 10. Right, so here is our weighted sum, and now we want to convert this into hex, right? 12, the decimal number, is C in hex. 1 in decimal is 1 in hex, and 10 in decimal is A in hex. So the number is C1A, right? Or the CIA. If you ever wonder to elders listening into our WebEx meetings, right? There may be a friendly CIA agent listening in. Hello, hello, right? Well, if you didn't know it yet, the decimal encoding of CIA happens to be 3098. I apologize to all other agencies on this planet who are listening in. You got to do the conversion yourself, right? Interrupt handed. There are shortcuts to doing conversions, in particular between hex and binary, that are called bit grouping. And let me convince you why this is so convenient to do that you never want to forget it whenever you want to convert between hex and binary, right? The observation is that one hex digit, right, which can represent 16 different numbers, in decimal 0 through 15, in hex 1, 0 through F, right, can also be represented in binary by exactly 4 bits, right? 4 bits also allow you to encode 16 different numbers in decimal, the same numbers, 0 through 15. Right? In binary 0, 0, 0, 0 through 1, 1, 1, 1. Okay? And that particular observation simplifies the conversion between binary and hexadecimal numbers as shown here in examples, right? If you want to convert 4AF as a hexadecimal number into binary, we simply start, best done from right to left, by converting the hex number, the hex digits, into binary, right? F hex equals 15 decimal equals 1111 binary. A equals 10 decimal equals 1010 binary. And 4 equals 4 decimal is 100. Right now, there is a snag here. If we deal with 4-bit numbers, there will be a leading 0 associated with the group of 4 bits that represent hex digit 4, right? That leading 0 doesn't add to the value of our binary number, so you may just rub it on the floor, right? And collect the remaining bits, and those constitute the binary number. No calculation done except converting digits to binary numbers, right? The same principle applies the other way about, right? If I'm giving you this long string of zeros and ones, right, and you want to convert it into a hex number, start right to left, right? Take the first 4 bits, 1111, right? that's an F in hex. The next 4 bits, 1010, that's A in hex, and the next 3 bits you may want to extend to complete a group of 4 bits. Typically, when you do this manually, you just do it in your head, right? Rather than writing it down. But in digital machines, you will actually have to supply such a 0 explicitly by grounding a wire. Right? Now, in your head, you know that 100 equals 4, S is 0100. So this string in binary is 4AF in hex. Okay? And I leave it to you to check out whether bit grouping also works for the binary octet conversions for that back. The problem set gives you a chance to think about it. One more slide on terminology so that we're all on the same page when talking about binary numbers, right? We distinguish bits, bytes, and nibbles when we refer to the strings of zeros and ones, right? These 1001110 bits are organized as a group of 8 bits into 1 byte. And the least significant bit of that 1 byte is the bytemost bit associated with position 2 to the 0, right? The most significant one is associated with position 7 and weight 2 to the 7. Right? So we call these 2 distinguished ends the least significant bit, or LSB, and the most significant bit, MSB. Right? If we look at a byte of 8 bits, we may also look at hexadecimal numbers, right? Where 2 hexadecimal digits form 1 byte. So analogously to referring to the least significant and the most significant bit in a byte, we may refer to the least significant and most significant byte in a hexadecimal number. 1 hexadecimal number is represented by 1 byte, so the least, 2 hexadecimal digits are represented in 1 byte. And in this particular example, the rightmost 2 hex digits, D7, are also the least significant byte, and the leftmost 2 hexadecimal digits are the most significant. Now, since 2 digits represent 1 byte, we may want to refer to the most significant and the least significant hex digit. And to make that easy, we introduce a grouping of bits in between the bits and the bytes that is a nibble that refers to 4 bits. And 1 nibble of 4 bits can also be represented by 1 hexadecimal digit. So if we are given a hexadecimal string of digits, the least significant hexadecimal digit is also referred to as the least significant nibble, and the most significant hex digit also as the most significant nibble. Next, let me look into operating, and the simplest operation on numbers is addition. Right? Before we look into binary addition at the bottom half of the slide, let's first recall how we add 2 decimal numbers. Right? We add 2 decimal numbers, 3,734 and 5,168, by aligning the numbers in the ones column, right? And then the tens, 100s, and 1,000 columns go towards the left. Then we add the numbers digit by digit, starting in the ones column. And 4 by 8 is 12. That is not a digit, but it's a two-digit decimal number. The 10 of the 12 belongs into the tens column. So we carry 110 over to the tens column. 1, 2 is the 12, right? We add the numbers in the tens column, including the carry. 3 plus 6 plus 1 is 10, which is 0 in the tens column and 1 in the 100s column, 1 carry. Right? 7 plus 1 plus 1 is 9. There's no carry, that's just a single digit, and 3 plus 5 is 8. So the sum of our numbers is 8,902. We do exactly the same thing in binary, right? Except that the values of the columns are now the powers of 2, right? We align the two numbers that we want to add, 1011 and 11 in the ones column, right? Just to be vigorous, I zero extend, I prepend leading zeros to the 1, 1, so I have something to add in the 4th and the 8th column, right? And now I add the bits column-wise from right to left, starting in the least significant column. 1 plus 1 is 2, all right? What is 2? It is more than 1, so it's not a bit, it's a binary number. And as a binary number, we encode it as 1, 0. So I have a carry of 1 going into the 2's column, and 0 for the sum bit in the 1's column. If we add the bits in the 2's column, 1 plus 1 plus 1 is 3, right? 3 is not a bit, it's larger than 1, right? And if you encode 3 as a binary number, right, it's a 2-bit number, 1, 1. 1 times 2 to the 1 plus 1 times 2 to the 0 is 3. So we have 1 carry that goes now into the 4th column, and 1, 1 that goes into the sum field. The 4th column now at 0, 0, 1 is 1. That is 1 bit without generating a carry, and the 8th column has 1 plus 0, 1 again without generating a carry. So the sum of 1, 0, 1, 1 and 1, 1 is 1, 1, 1, 0. You want to check yourself, do it in decimal, right? 1, 0, 1, 1 is 1 plus 2 is 3 plus no 4 plus 1, 8. 3 plus 8 is 11 plus 3 is 14. And the sum is 0 times 1 plus 1 times 2 plus 4 plus 8 is 14 as well, right? 8 plus 4 plus 2 is 14. All right. So paper and pencil addition is a breeze in any number system with any base, right? Base 2, base 10, base 16, base 8. It works exactly the same way. Now, there is that one special case that becomes important when we build digital circuits, right? And that is the overflow case. Overflow simply means if I am giving you 2 decimal numbers and sum them up, there is a ripple out of the most significant position, right? That 1, so that the sum is a 5-digit number, although both summands are just 4-digit numbers. The same thing happens in binary, right? If I add these 2 binary numbers, they are 4-bit numbers, I get a 5-bit sum. That one that is carrying out beyond the length of the summons is called the overflow bit. It carries out of the most significant bit position, right? Now, in principle, that's perfectly fine, right? Two smaller numbers will definitely add up to a bigger number. So from that perspective, there is nothing wrong with that overflow effect. However, when we build digital systems, we need wires to carry the individual bits as voltages, right? So if we build a digital system that is capable of manipulating 4-bit numbers, we build a Q equals 4-bit system, right? And then we're going to build an adder, and that adder will produce a 4-bit sum. Right? And if we feed these two numbers, 1011 and 0110, into our adder, we get out a 4-bit sum. Right? The problem is that sum is wrong. Right? The sum of 8 plus 2 plus 1, 11, and 4 plus 2, 6 should be 17. Right? What the adder will output is a 1, right? And that is a major problem, right? By just ignoring the carry out and not being able to represent 5-bit numbers in a 4-bit digital design can lead to disasters, right? Like rockets falling out of the sky or passenger airplanes crashing. This is definitely not unheard of. Digital systems got to be taken with care exactly when it comes to such basic effects like overflow in an addition. All right, now let me spend a few minutes on negative numbers. So far, we have only looked at positive numbers or non-negative numbers, including 0. We also need to deal with negative numbers if we subtract, for example. Right? And there are various different ways of representing binary negative numbers that I will just overview here on this and the next slide. You can work yourself through the math that actually tells you in detail how we represent a number n as a particular representation, starting with the sign magnitude representation, or S/M for short, right? Name suggests that a binary number that is represented as a sign and a magnitude designates the first or the most significant bit as the sign bit and interprets the rest, the remaining bits, as the unsigned magnitude. On the top right, you have two examples, right? If you are given a 4-bit binary number, simply interpret the most significant bit, 0, in the first equation as the positive sign, and the remaining 3 bits give you the magnitude of the number. So 101 is 4 plus no 2 plus 11 is 5. And we interpret that 4-bit binary number as a positive decimal 5. If we flip that most significant bit, 1 shall represent a minus sign with magnitude 5 again. So binary number 1101, we would interpret as negative decimal 5. Right? That's easy enough and simply enables you to deal with positive and negative numbers. However, that's a bad choice, and as we'll see later. It makes sense to complicate things first before it gets easier again. Right? And the complication starts with the notion of the complement of a digit. I denote the complement of a digit A with an overlining bar, right? So the complement of A of a digit A with base B is generally defined as B minus 1 minus A. Right? Let's exercise that for decimal digits. Right? In decimal, the base is 10. So here is an example where the digit that we want to compute the complement of is 3. The complement of 3 is 10 minus 1 is 9, minus 3 is 6. Right? So the ones complement of number 3 in decimal is the decimal 6. We move on to the binary numbers, where the base is 2, right? The complement of A equals 1 is 2 minus 1 is 1, minus 1 is 0. And the complement of the other binary number, binary digit, bit 0 is 2 minus 1 is 1, minus 0 is 1. Right? And these are all the cases we have in binary numbers. We have 2 bits, 0 and 1. And observe, computing the complement of a bit simply means toggling the bit, right? Flipping the bit from 1 to 0 and from 0 to 1. That is an easy operation even to implement in hardware, right? Now, before we use that, let's first extend the notion of a complement to larger numbers, multi-digit numbers. Right? If we are given a number n, capital N, with q digits, then the complement of n, the ones complement of n, is defined as the base to the power of q minus 1 minus that number, right? The only change compared to the complement of a digit is to replace the 1 in the exponent of b with a general q, right? Now, it turns out that in the binary system, forming the ones complement, as the name suggests, is flip every single bit. Means the complement of 0110 in binary is 1001, right? And vice versa. Right? You can go back. The complement of 1001 would be 0110. How do we use the complement to interpret a 4-bit binary number as a negative or a positive number? Where we again use the idea of the sign bit, but now we interpret negative numbers differently. If the sign bit, the most significant bit of a qubit number, which is bit A sub q minus 1 is 0, then we interpret the number as a positive number. So that is just n. If the sign bit is 1, we interpret the number as a negative number, and the magnitude of the number is the ones complement of the number. We'll see examples in a second. It turns out that the ones complement doesn't get us exactly where we want to be. There is a second form of complement, the twos complement, right? Second in row. And the twos complement is simply defined as the ones complement plus 1. Right? If we use this definition, we can interpret a number capital N as positive or negative by looking at the most significant bit, the sign bit again. And if the sign bit is 0, we interpret the number as a positive number, n. And if the sign bit is 1, then we interpret the number as a negative number whose magnitude is the 2's complement, and the 2's complement is the 1's complement plus 1. There are other number representations, for example, the bias number representation, right? That is particularly simple at the first glance. The bias representation of a number capital N simply adds a constant bias capital B to N, and the resulting number is interpreted as the number in bias format. Now, in general, you want to pick that bias B such that all the sign numbers, positive and negative numbers N, after adding the bias should become positive or non-negative numbers, to be precise. Right? If that is the case, you don't need a sign bit any longer, right? Your bias representation has just non-negative numbers, and if you want to compute the actual value of the bias number representation, you gotta subtract the bias B from N bias again. Right? This particular representation is used in floating point numbers to encode the floating point exponent. Right? For integer binary numbers, it is not used because adding the bias is an expensive operation for another thing. All right. So let me compare these 4 different number representations for 4-bit binary numbers, right? Those are the binary numbers in range 0 through 15, but now interpreted as sign numbers. So what you see here, I have ordered the binary numbers not starting at 0, but the 0 is now somewhere in the middle, right? And I've done that because we interpret these binary bit strings, 4-bit strings, now as signed numbers. In the signed magnitude representation, the 0 is 0, 1 is 1, up to 7. These are all the binary numbers with a 0 sign bit. And the negative numbers in the sign magnitude system grow down, right? You interpret 1, 0, 0, 0 as a negative number with magnitude 0, right? So this is a negative 0. This one here is a negative number with magnitude 001 is decimal 1, right? All the way down to 1, 1, 1, 1, right? This is a negative number with value 1 plus 2 plus 4 is 7. So the overall value is negative 7. In the 1's complement, you do a similar thing, right? As long as the most significant bit, the sign bit is 0, you just interpret the number by the magnitude of the remaining 3 bits. And if the sign bit is 1, you compute the 1's complement. So the 1's complement of 1, 0, 0, 0 is 0, 1, 1, 1. 0, 1, 1, 1 has decimal value 7, and you interpret binary string 1, 0, 0, 0 as the negative magnitude 7, number negative 7, right? This string here, 1, 0, 1, 1, is a negative number because the most significant bit is 1. You compute the value of the negative number by taking the complement, the 1's complement, which represents the magnitude, right? It's bit string 0, 1, 0, 0. The value of the magnitude is 0 times 1 plus 0 times 2 plus 1 times 4 is 4. So the negative number has value negative 4. Right? all the way down to 1111. It's a negative number because the most significant bit is 1. You compute the value of the number by taking the ones complement, gives you all zeros. So the magnitude is 0. The value of the number is a negative 0. As you may see here, right, we got 2 zeros in the sign magnitude representation. We also got 2 zeros in the ones complement. The 2's complement fixes that. Right? The 2's complement is the skillful deal where the positive numbers or non-negative numbers are given as before, but we add 1 to the 1's complement for the negative numbers in order to avoid a second 0. So now the 2's complement has a negative number range from -1 down to -8, rather than from -0 to -8 for the sign magnitude and ones complement numbers. The biased representation is shown on the rightmost column, right, where the bias has been chosen to be 7, and the value of the binary number is the magnitude of the binary number minus bias 7. You can try that yourself. That is actually rather straightforward. Okay, brief discussion of these different formats, right? Sign and magnitude as well as the ones complement have 2 encodings of 0. That's considered wasteful, right? And it actually introduces complications when it comes to building digital systems. There is one more snag in the sign and magnitude representation that makes it a complete showstopper. We do not want to use sign magnitude representation of numbers. Here is an example where things go completely wrong in an addition. If we add -6 and 6 and represent the -6 and the 6 in sign magnitude with our usual paper and pencil addition, we get out a number that is not equal to 0. That's really bad. Okay, so the sign magnitude representation definitely doesn't count it as a candidate for digital system implementation. The 2's complement has unsymmetric ranges, right? It goes from -8 to 7 for 4-bit binary numbers. Right? And for bias, it goes from -7 to 8, right? But it has 1 0 representation only, and addition works just fine. So we consider the asymmetry in the range just as a beauty spot that we can live with, though. There is one little complication with the 2's complement. To form it digitally, you probably want to flip all the bits, means form the ones complement, but then you still need to add the 1. Right? At first glance, that addition of a 1 is a tricky thing to do. Right? It's almost as tricky as adding an arbitrary bias B. Right? But as we will see, when we build adders, adding a 1 to a number actually comes for free. So this turns out to be easy. Forming the ones complement in digital logic is easy. Adding an arbitrary number larger than 1 is not easy. That will definitely cause overhead. And as a result of comparing all these different representations, all of today's computers, there may be some exceptions, of course, but in general, all of the digital computers that you and I are using right now represent signed fixed point numbers using the 2's complement format. Signed means the numbers can be interpreted positive and negative. Unsigned means non-negative only. All right, 2 examples, right? If you want to encode decimal number -3 as a 2's complement binary number with 4 bits, with Q equals 4 bits, right? Because your machine may represent all numbers with 4 bits, right? You convert the magnitude of -3 in step 1 from decimal to binary, right? The magnitude of -3 is 3, has binary representation with 4 bits, 0, 0, 1, 1. You form the ones complement by flipping our bits, right? 0, 0, 1, 1 turns into 1, 1, 0, 0, and then you add the 1, right? And doing the addition by paper and pencil method gives you the number 1, 1, 0, 1, and that is the binary representation of negative decimal number -3. You notice that because the sign bit of the binary representation is 1 rather than 0. The other way around works surprisingly similar. If we want to know the decimal value of binary number 1001, you notice that the most significant bit, the sign bit, is 1, so that must be a negative number. Right? To obtain the magnitude of the negative number, its absolute value, you first form the ones complement, right? Flip our bits, 1001 turns into 0110. Add 1, and you get number 1 plus 2 plus 4 is 7 decimal. And you conclude that the decimal value of signed 4-bit binary number 1001 is -7, right? And it turns out that in general, the negation works in both directions. Positive to negative or negative to positive can always be done by forming the 2's complement. And these 3 steps recipes shown on these particular examples are what you want to do. One last slide that is very quick, bit size extension. Right? When we build digital machines and we want to represent numbers, binary numbers with different numbers of bits, we want to be able to convert between those numbers, right? Let's assume we have a qubit binary number and want to turn it into a p-bit binary number where p is larger than q, means we want to take a narrow number and extend it into a wide number. Well, there are 2 ways to do that easily. One is called zero extension, the other is called sign extension. Zero extension means prepend the qubit number with p minus q zeros. Example, if we are given a q equals 4-bit number, 0011, and we want to turn it into an 8-bit number, prepending 8 minus 4 equals 4 zeros does the job. Now, if we do the same for number 1001, just prepending 4 zeros, you see already that that might cause problems, right? If we interpret this number as an unsigned number, the value is 1 plus 8 is 9, and the value of this 8-bit number is still 1 plus 8 is 9. However, if we interpret this 4-bit number as a signed number, the value is negative because the sign bit is 1. And if we zero extend this number, the sign bit will become 0, right? So this 8-bit number cannot have the same value than this 4-bit number. This is a positive, this is a negative number, right? So remember, blindly zero extending numbers from 4 bits to 8 bits or P or Q to P bits is dangerous. If you interpret the numbers as signed numbers, it works fine if you consider the numbers to be unsigned. Now, to deal with signed numbers, the sign extension does the job. You don't prepend zeros, but you prepend the sign bit, the MSB of your qubit number, p minus q times. Right, here we have our 4-bit number. We want to extend it into an 8-bit number. The sign bit of the 4-bit number is 0, and we prepend that sign bit 4 times to our 4-bit number to get the 8-bit number. We do the same thing here in the second example for number 1001. Prepending the sign bit 1 4 times obviously also gives us a negative number, right? This one gives us a positive number, this one gives us a negative number. And I leave it up to you to convert these binary numbers, right? And see that the sign extension preserves signed numbers. And you also may want to check that 0 extension preserves unsigned numbers. But they change the value if we interpret the numbers the other way. All right, and that concludes lecture 1.